Okay, so today I want to talk about the reduction of the second law of thermodynamics. Oh, it won't let me move. Maybe now. Okay, there we go. So the second law has kind of an exalted status amongst the different laws of physics. So in his famous paper about the two cultures, C.P. Snow claimed that it was the kind of scientific equivalent of having read a work of Shakespeare. Eddington said that, you know, if your pet theory turns out to be empirically inadequate, that's not so bad as compared to contradicting the second law of thermodynamics. And in a similar vein, Atkins says that the second law is one of the all-time great laws of science, for it illuminates why anything from the cooling of hot matter to the formulation of a thought happens at all. And so one of the questions that this quote raises is what the scope of thermodynamics is. So what type of systems do we think that it applies to? And I'm going to touch on this briefly later, but the main focus of my talk today is going to be about the reduction of the second law of thermodynamics. So outside of philosophy of physics, thermodynamics is often taken to be the kind of like paradigmatic case of a successful reduction. But within philosophy of physics, there's been some skepticism, most prominently by Scar and Batterman. So for instance, Batterman says, it is almost surely the case that thermodynamics does not reduce to statistical mechanics, according to the received view of the nature of reduction in the philosophical literature. So I think there's two things. Firstly, whether you think a particular case of reduction is going to be successful or not is going to depend upon how you conceive of reduction. So in particular, how many additional assumptions you think you're allowed to have. So earlier we saw that Orley wanted to have very few additional assumptions added in. Some other views may allow more additional assumptions. And the other thing is not only how you conceive of reduction, but also like how you conceive of the two different theories. So what's new here? So I'm going to claim that often the focus when thinking about reduction has been on the spontaneous approach to equilibrium. And this is really the minus first law, which I'll come to explain in more detail in a minute, rather than the second law itself. And when we focus on the second law, we'll see that we need to consider the kind of very unusual nature of processes in thermodynamics. So often people say that thermodynamics is kind of a bit of an ill-named theory in that it really should be called thermostatics or something instead. Okay. And as a methodological point, I'm going to discuss how functionalism can be useful for securing reductions. So firstly, on to functionalism. So the view that functionalism is that to be X is to play the X role. And a typical example of this is being locked. So being locked can be realized by a variety of different mechanisms: D-locks, padlocks, combination locks. And functionalism has become more popular in philosophy of physics in the last 10 years or so. So for instance, we have Eleanor Knox's space-time functionalism. Lamb and Ruthrick argue that functionalism might help us understand how space-time emerges from a fundamentally non-spatiotemporal theory of quantum gravity. Albert and Ney want to functionally recover the three-dimensional world from the three-dimensional configuration space of the wave function that was discussed at the last workshop. Wallace wants to say that macroscopic patterns in the wave function that behave like tigers, i.e. that function like tigers, are tigers. And finally, Menon and Callender say that temperature and entropy are multiply realized functional kinds. So why has functionalism become more popular in the philosophy of physics? I think that this is because functionalism is quite helpful for understanding inter-theory relations. So in the quantum case, Albert, Ney, and Wallace want to recover the behavior of macroscopic objects described by classical theory, i.e. described by like some higher level theory, from the underlying, more fundamental quantum description. And in the case of space-time functionalism, the aim is to compare different spacetimes across different theories. So again, we have kind of a case of intertheoretic relations. And in particular, I think that functionalism is a useful strategy for reduction. This is for the following reason. So if the higher level concepts are functional role concepts, then the realizer, i.e. the reductive basis, just has to play the same role, i.e. have the same behavior. And as a consequence, certain differences won't matter. In particular, those differences which don't contribute to having the same behavior or don't matter for playing the same role. So for instance, whether the lock requires a key or what color it is or what brand it is, doesn't matter for it filling the role of locking things. And in the case of thermal physics, so Sklar, one of the skeptics about the reduction of thermodynamics, says that he has this worry that temperature equals mean kinetic energy in an ideal gas. He worries that this is kind of a problematic thing because you're identifying a non-statistical quantity with a statistical quantity, and so the two things differ. But according to the functionalist, these two different levels can differ in certain ways, provided that mean kinetic energy, provided that being statistical isn't, non-statistical is not a kind of crucial part of the temperature role. But of course, I think that the kind of controversial thing is going to be over cases like this. So is being non-statistical a kind of key part of the temperature role? And I think that the controversy is going to reside in kind of cashing out which differences don't matter. So the hard work is in sort of spelling out the roles. I think the kind of substantive part about space-time functionalism is saying that the role of space-time is to define inertial trajectories. Maybe your heart was sinking over the last few minutes as I started talking about functionalism. You thought, oh no, you're in for 45 minutes of functionalism. Don't worry, there's a kind of reassuring thing to be said, which is this. So functionalism emphasizes that there might be differences between the entity to be reduced, so the top theory, T sub T, and the reducer, the bottom underlying theory. But this is just kind of like a standard point in the reduction literature. So for instance, in the Nagel-Schaffner account, you only need to deduce an approximation or a close cousin of your original theory. So if you really hate functionalism, every time the words realizer come out of my mouth, just think reductive basis. And there's going to be one caveat to this later on, but I'll come to that later. Okay, so the functionalist strategy for reducing the second law is going to be to articulate the functional role and then find the realizer within statistical mechanics. Okay, so the plan for this talk is that first I'm going to discuss the nature of processes in thermodynamics. Following your UFFINK, I'll distinguish 3 different types of time asymmetry in thermal physics. I'll quickly remind you about the second law, and then I'll articulate the role of the thermodynamic entropy, which is going to be this. For a thermally isolated system, it increases in non-quasi-static processes, but is constant in quasi-static processes. And I'm going to talk more about these quasi-static processes in a second. Then I'm going to emphasize how this role differs from what Craig Callender's called the traditional holy grail of the reduction. I'll then search for the realizer in quantum statistical mechanics, and I'll claim that the Gibbs entropy plays this role. But the Gibbs entropy has been the kind of unpopular entropy compared to its cousin, the Boltzmann entropy, at least in some circles. So I'm going to end by defending the Gibbs entropy from what's sometimes been called the ensemble objection. Okay. So to start off. So equilibrium is really at the heart of thermodynamics. It's a presupposition of the theory, and equilibrium is the state where the macro parameters are no longer changing in time. And it's a presupposition of the theory that systems will end up at equilibrium. In fact, this is such a central part of thermodynamics that it's even been given the honorific of being a law. So Harvey, Brown, and UFFINK have termed this the minus first law, that an isolated system in an arbitrary initial state will spontaneously reach a unique state of equilibrium. And they say, you know, this is so central to thermodynamics that whilst we call it the minus first law, it could in fact be called the minus infinite law. Okay, so thermodynamics is not a dynamical theory in the usual sense. Often we have the kind of kinematics, the kind of space of possibilities, the kind of possibilities of the ways your system could be, and then you have the dynamics, which tells you how your system kind of traces through those different possibilities over time. But in thermodynamics, the state space is that of equilibrium states. So according to the minus first law, your system is going to reach an equilibrium state, but then what? Well, by the definition of equilibrium, nothing. Once your system's reached equilibrium, it's just going to sit there indefinitely. I mean, of course, this is kind of an idealization. So it's more that systems for which thermodynamics is a kind of successful description behave as if they're going to be in equilibrium for all time. So in order to have any change or process to occur once your system's in this equilibrium state, there must be some kind of intervention on your system. So you've got to kind of slowly squeeze your system with a piston, or whip out a partition, or turn on a magnetic field. So in the case of the dual expansion of the gas, so taking out a partition and letting your gas uncontrollably expand, the system's no longer going to be in equilibrium. And thermodynamics is silent about what happens away from equilibrium. And so the state of the gas is not going to be represented in this equilibrium state space, but according to the minus first law, it's going to return to a new equilibrium state. So it's going to be represented by a diagram like this, where maybe like P1 is the earlier state and P2 is the later state. But this has led to a kind of controversy because whilst the dual expansion is represented by those 2 points, is not represented by this kind of, maybe I can kind of circle it, yeah, by this kind of figure here, which is a curve throughout the equilibrium state space. So that's a kind of series of different points through in that space. And these curves in equilibrium state space have been the source of a recent controversy between John Norton, Giovanni Vellante, and David Levis. And this controversy sort of stems back to the work of Tatiana Ehrenfest-Asafaneva, who's actually got a recent, there's going to be a recent book about her contributions that have been slightly overlooked in the history of physics coming out soon. Okay, so how should we understand these curves? So they represent what these quasi-static processes. And the idea is that we're going to have a series of very small and very slow interventions that's going to mean that the system approximately traces out the curve. So the idea is that I kind of insert my piston very slowly. That is going to take my system away from equilibrium, but hopefully it will return to a new equilibrium state not very far away from the one it started at. So it sort of traces out the curve in this way. And because the curve can be traversed in either direction, there's a sense in which it represents a reversible process. But there's these different types of reversibility in thermal physics. So the first type is the kind of familiar type of non-time reversible invariance. So according to this type of reversibility, there's some kind of map which takes you from possible solutions to the laws or equations of your theory to other possible solutions. And if it doesn't take you to other possible solutions, then it's a failure of time reversible invariance. The second type of reversibility in thermal physics is these quasi-static processes. And the third is the idea of recoverability, which I'm going to describe these both in a bit more detail now. In the figure there's a kind of picture of a Carnot cycle. These are kind of reversible. These curves represent these quasi-static processes are reversible in this, that the arrows can be drawn in either direction on the curve. And traveling in one direction, so from going from A to B, that's going to be an expansion of my gas. It's not going to be the same thing as just traveling from B to A. You're going to have to do 2 different interventions. One, you're removing a piston, and the other, you're inserting one. And one slight caveat is this all assumes that there's going to be no friction in the piston. Okay. Now to the third type of reversibility, irrecoverability. So recoverability is, means that the process in question can be fully undone. This is its initial state with no effect in the environment. But to do this, the system needn't retrace its steps. It could take a different path back to its earlier initial state. So a process is going to be recoverable if, and I apologize slightly for the notation, S doesn't stand for entropy, but stands for the system. So the initial state of the system and the environment is taken to the final state of the system and environment by process P. That process P will be recoverable if there's some other process P star that takes them both back to their initial state. Okay, so now on to the second law. So just to very briefly remind you about the second law, it comes in various different statements. There's the QUASI statement and the Kelvin statement, which is that it's impossible to perform a cyclic process with no other result than that heat is absorbed from a reservoir and work is performed. And there's of course also the Carnot statement that no engine is more efficient than a Carnot engine. And from these statements of the second law, we can define a new quantity of state, the entropy. So we consider different heat flows at temperatures in a quasi-static reversible cycle, and then we can define this new function, entropy. And for an adiabatic process, i.e. for a thermally isolated system in which there's no heat flow, the change in the thermodynamic entropy is either going to be greater than 0 if it's a non-quasi-static process, or it's going to be 0 if the process is quasi-static. So if it's one of these curves in the equilibrium state space. So I distinguish these different types of reversibility. Which type of reversibility does the second law describe? The second law describes the irrecoverability of certain initial states if the process is a non-quasi-static process. So I think the kind of irrecoverability is the type of irreversibility that really captures the imagination, in that it's the kind of process that we seem to see in lots of cases all around us. So from spilt milk to the kind of failure to be able to recapture lost youth, to unfortunately smashing wine glasses. These seem to all sort of capture the fact that we can't get back to those initial states. They seem like irrecoverable cases. And I think this is kind of what Atkins had in mind with that opening quote about the second law being involved in the formulation of a thought. So there's this question of like, does the second law really apply to these processes? And I think there's a slight reason to be a little bit cautious and maybe not go for a kind of thermodynamic imperialism, in that it's not entirely clear that we can assign a thermodynamic entropy to these processes, because it's not clear that there's an available equilibrium state space or quasi-static processes. So Kirchhoff warns that the increase of entropy is conditional on the existence of quasi-static transitions. Now, of course, the thermodynamic entropy is a state function, so it's perfectly well defined during non-quasi-static processes. But the point is that you need these quasi-static processes in order to define the entropy in the first place, to calculate it in particular cases, and also to provide the lower bound. So it's slightly unclear to me, and I'd be interested to know what you think later on in the question time, whether the second law really applies to these in anything more than a really metaphorical sense. So whilst irrecoverability is like maybe the more glamorous notion of irreversibility, I think quasi-static processes are also really central, and they're going to be really central to the reduction of the second law. Okay, so now I'm going to turn to statistical mechanics. So in thermodynamics, the distinction between heat and work is really central. But finding this distinction in statistical mechanics is at best complicated and at worst unnatural or anthropocentric. And this idea kind of stems back to Maxwell. So Maxwell claimed that the distinction between heat and work is one of disordered and ordered motion, which is not a property of material things in themselves, but only in relation to the mind which perceives them. So consequently, the Kelvin formulation doesn't have an obvious correlate within statistical mechanics. And because of this, the usual way that reduction goes is that people try and find a realizer of the thermodynamic entropy in statistical mechanics. And that seems the key to finding a reduction. And Callender kind of disparagingly calls this the search for the Holy Grail. He says the thing that people are focused on is finding a statistical mechanical function to call entropy and establish that it's non-decreasing. I'm going to criticize this Holy Grail in just a second, but first I'm going to consider the nature of the reductive project at hand. So recall earlier I had this distinction between the minus first law and the second law. So the minus first law was about the spontaneous approach to equilibrium from non-equilibrium, and the type of irreversibility that it embodies is the non-time reversal invariance type, versus the second law, which tells us about entropy differences between equilibrium states. And that describes kind of irrecoverability during non-quasi-static processes. And there's this nice paper by Josh Lukatz, who emphasizes that the kind of finding the microphysical underpinning, i.e. the reduction of these two laws, is two distinct projects. So the H theorem, the coarse-graining approach, the combinatoric argument are all approaches for understanding the approach to equilibrium, i.e. the minus first law, rather than quasi-static interventions on equilibrium states. But of course, given how the minus first law is baked into the nature of quasi-static processes, so earlier I said that you do a small intervention, your system goes away from equilibrium but returns by the minus first law, the two projects are going to be connected, which we'll see later. But the key point is that even if we manage to resolve all the controversy about coarse-graining, the combinatoric argument, the H theorem, and we kind of settle on something once and for all, there's still going to be this further project to reduce the second law. Okay. So according to the old Grail, what we need to do is find a non-decreasing function to call entropy, but I think this is both too weak and too strong. So it's not the right role. It's too strong because the thermodynamic entropy is only defined at equilibrium. So there's going to be no problem if the statistical mechanical entropy decreases away from equilibrium. And secondly, it's too weak because we want it to increase in the right situations as well. So I'm going to say that the thing that we really want to find is the new Grail, which is to find a statistical mechanical realizer, which is increasing in non-quasi-static adiabatic processes, but is constant in quasi-static adiabatic processes. Okay, so where have we got to? So we found the required role, or the new Grail, which is for thermally isolated systems. The thermodynamic entropy increases during non-quasi-static processes, but remains constant in quasi-static processes. And having outlined the role in thermodynamics, we now need to search for the realizer in statistical mechanics. So to do this, I'm going to take a Gibbsian approach, but later I'm going to defend the Gibbs entropy, but doing so won't involve any criticism of the Boltzmann entropy. So it could, it's open that the Boltzmann entropy could also play this role. So in order to do this, I'm going to first consider how to make interventions on external parameters in quantum statistical mechanics. And then I'm going to show that the Gibbs entropy will play the right role. It's going to be constant in quasi-static processes, adiabatic processes, but increase in non-quasi-static adiabatic processes. And then I'm going to come full circle and return to heat. Okay. So in quantum stat mech, like classical stat mech, thermal equilibrium is represented by the canonically distributed state. And whilst in classical statistical mechanics, the canonical distribution is a probability density distribution over the phase space, in quantum stat mech, the canonical distribution is a density matrix, where this is a statistical mixture of energy eigenstates, where the probability of being in any given eigenstate depends exponentially on the energy eigenvalue of that state and the temperature. And this is canonical distribution is going to come into this definition here of the Gibbs entropy, where here that equation 4 is the kind of quantum analog of the familiar classical Gibbs entropy. Okay, so in order to change external parameters in quantum statistical mechanics, what we're first going to do is start off with a system at the initial time, which is T0 in the canonical ensemble. And so during this time, the Hamiltonian is time independent. The external parameter, which I'm going to take in this case just to be the size of the box, for instance, is going to determine the potential energy. And so changing an external parameter, like the volume of the box, or like push it in with the piston, is going to change the Hamiltonian during that intermediate time. So at the beginning and at the end, we've got a time-independent Hamiltonian, and in between, we have a time-dependent Hamiltonian. The energy eigenstates in the canonical distributed state are eigenstates of the initial Hamiltonian and are so unchanging in time. But in the intermediary time, each eigenstate is going to evolve to a new state, where I've written it in this general form to indicate that it might not be in an energy eigenstate of the new Hamiltonian, and it might also be changing in time. So the goal is going to be to show that if the change to the external parameter is quasi-static, then the Gibbs entropy is constant. But if the intervention is non-quasi-static, it's rapid, I just yank the piston out, then the Gibbs entropy is going to increase. Okay, so first to the quasi-static change. We saw earlier that a quasi-static process requires that the system is very close to equilibrium at each stage. So in quantum stat mech, that's going to be that it needs to be approximately in the canonical distribution. So each pure state, so the initial energy eigenstate, in the statistical mixture, it's going to evolve under the time-dependent Schrodinger equation, carrying its original weighting. So that was the e to the power of the energy eigenvalue and temperature, carrying this probability of being in that state with it. But the question is, why think that this density matrix is going to be still canonically distributed as I pull out the piston? So for it to be canonical, it needs to be a statistical mixture of energy eigenstates of the time-dependent Hamiltonian, and the probability needs to depend on the energy eigenvalue. And the first condition is going to be ensured by something called Ehrenfest's principle, which is also known as the quantum adiabatic theorem, which is Sometimes a slightly unfortunate name because obviously in this case, adiabatic means very slow, whereas the rest of the time in thermodynamics, adiabatic means thermally isolated. Okay, so excuse the large amount of text about to hit you, but this is what Ehrenfest's principle is. So the idea is that if the energy eigenstates of the time-dependent Hamiltonian are non-degenerate, and your system initially starts in an energy eigenstate, and we change the external parameter very slowly, then in the intermediary time, it's going to be approximately in an energy eigenstate during that time. And in the limits where a finite change in the external parameter occurs over an infinite time interval, then it's very nearly in the canonical state, becomes it is in the canonical state. Sorry, it is in the energy eigenstate. Whether it's in the canonical distribution, I've yet to establish. Okay, so why I think that Ehrenfest's principle holds? Of course, infinite time limits are contentious, and they only hold approximately in real life situations. So I think the way to think about it is that just like in the thermodynamic case, an intervention counts as being slow enough if the time taken to do that intervention is much larger than, say, the characteristic timescale of the system you're looking at. So it could be like very long compared to the time taken for one of your gas molecules to go from one side of the box to the other, for instance. So in that sense, it's sort of, yeah. Okay, so if Ehrenfest's principle holds, then the energy eigenstates are going to be taken to new energy eigenstates. But the question is, so that means that so on this graph here, you've got all these different possible energies that the different states could have with the different probabilities attached to them. And you're going to go from energy eigenstates to other energy eigenstates. So there's going to be no kind of crossing of these lines, so it can't like redistribute itself into something like a Gaussian or something like that. But the question is, why think that it's going to be canonically distributed? Why do you think, why are you going to be able to have this exponential? Why not just think it's some other kind of monotonically decreasing distribution? So the answer is that it will be, provided that this particular relation holds. So there needs to be the right relationship between the earlier energy eigenvalues and the later energy eigenvalues. This term here was the weighting of each state. We can rewrite that in terms of what I've written here is 8, but sorry, that's a typo, that should say 6. Then we can see that we've got the right type of canonical weighting, but with a new temperature. So provided that the conditions of Ehrenfest's principle apply, and that what used to be called 8, but now it's called 6, holds, then the system will remain approximately canonically distributed with a changing temperature. And furthermore, and like crucially for this project, the Gibbs entropy will be constant because the dynamics are unitary. And I think this is kind of wholly unsurprising. The whole problem with the Gibbs entropy is working out how to make it increase. So that's the task of the next section, considering the non-quasi-static, so the rapid changes. So if I just yank the piston out, the system won't be in an energy eigenstate of the later Hamiltonian, and so won't be at equilibrium. So one way of putting this is that it's not going to be diagonal in the energy eigenbasis. But we assume that eventually the system will settle down to a new equilibrium. That's what we assumed with the minus first law. And of course, justifying this is super controversial. Should we think that systems approach equilibrium because of the H theorem, coarse-graining, combinatoric argument? My preferred approach is going to be this. I'm not going to try and convince you of this in this short time, but just to give you an idea, yeah, my preferred approach for justifying the approach to equilibrium is this coarse-graining in what I'm going to call the Zay-Swanzig-Wallace framework. And very briefly, the idea is that you start with the unitary dynamics, which is going to be defined by your Hamiltonian. You find a projector that kills off the off-diagonal terms and builds a master equation that's going to quantitatively describe the approach to equilibrium. So in the case of, say, the Boltzmann equation, you're going to have a projector that kills off all the 3 or more particle correlations and use that to build the Boltzmann equation. But in the absence of a concrete master equation, the pragmatic move in equilibrium stat mech is just to adopt a new canonical distribution with the energy eigenstates appropriate for the new volume. In other words, we're going to coarse grain. and where we assume that this is going to be a kind of legitimate move long after the parameters, the external parameters stopped changing. And crucially, that's going to mean that the Gibbs entropy increases because the probability distribution has been coarse-grained. Now, this is controversial, I suppose, and but there's nonetheless sort of harmony can reign, because even if you don't like this approach to thinking about the approach to equilibrium, all schools of non-equilibrium stat mech agree that the statistical mechanical entropy increases in the approach to equilibrium. So we've achieved our goal. We've got an entropy that increases in rapid non-quasi-static processes, but is constant in quasi-static processes. So I'll now briefly connect this to heat. So in thermodynamics, the relationship between heat and entropy is as follows. And the first law of thermodynamics gives us this equation here. And so the idea is, in statistical mechanics, we can find the relationship between heat and entropy. If the external parameter is changing slowly enough, then we can write it in a differential form as shown in equation 10. And where basically what happens is we recognize that differentials of things like the partition function are in fact things like expectation values of the entropy. Okay, and since these two equations represent the same functional interdependencies, the Gibbs entropy bears the right relation to heat. But there's one obvious difference, that we're dealing with expectation values. But I want to say that this is a feature, not a bug. It's not a problem that the kind of reductive basis that we found differs in some way from the original relationship. And that's because the variance gives us useful information about fluctuation phenomena. And this is partly because I see this as a good thing, because a successor theory often kind of improves upon the older theory. And this is the case in StatMech and thermodynamics. So StatMech is kind of the successor theory in some ways to the older theory of thermodynamics. And often a successor theory will limit the domain or scope of the older theory. And since Maxwell, everybody agrees that the second law can be violated. And so Maxwell says, hence the second law has been continued violated and to a considerable extent in any sufficiently small group of molecules belonging to a real body. But I think the important thing to notice is it's not that we think that the second law is therefore just like totally false and wrong. And if it was, we wouldn't be particularly interested in reducing it. We just sort of relegate it to the kind of rubbish bin of bad scientific theories. So clearly the second law gets something, captures something true about the world. It seems that we don't really have many greater than Carnot efficiency engines. And if we could have any hope of having a greater than Carnot efficiency engine, that would seem like a really useful thing for practical purposes in life as well. So how should we restrict the second law? The orthodoxy is that we must at least weaken it to a probabilistic statement. So fluctuation phenomena imply that heat can spontaneously flow from colder to hotter bodies with no other effect, but on average, there'll be no such net flow. And so a weakening of the second law to a probabilistic version, as reflected in the use of expectation values in StatMech, is a kind of an appropriate thing, I think. Okay. So the Gibbs entropy can play the right role. It increases in non-quasi-static processes, but it's constant in quasi-static processes. And furthermore, it's connected to heat in the right way. And I would say that the presence of expectation values is a feature, not a bug. Okay, so now to defend the Gibbs entropy. I think it's fair to say that the Gibbs entropy in some philosophical circles is less popular than the Boltzmann entropy. And the main, well, I would say the main objection to the Gibbs entropy is that it's an ensemble property rather than the property of an individual system. So often, instead of talking about often we talk about the canonical ensemble rather than say the canonical probability distribution. And this is because of the way that Gibbs originally described the canonical distribution. So he gave this kind of view that really when you're putting, so you have all your possible states of your system, one of which it's really in, then you put a probability distribution over that space of possible states. And what happens is the weight given to each point represents how many systems in an infinite imaginary ensemble of systems like yours are in that state. And so that's where the kind of ensemble terminology comes from. But and then people worry, well, hang on a second, how is this connected to you know, gases that thermodynamics talks about? This imaginary ensemble, it seems a bit suspicious. But I think that we can kind of demystify this, because discussing the ensemble is just a vivid way to give statistical mechanical probabilities a frequency interpretation. And of course, there are lots of different puzzles about how to understand statistical mechanical probabilities. But we needn't give, there's some particularly mystery mongering interpretations that we could perhaps rule out. So for instance, as an alternative to the kind of ensemble way of thinking about things, it's often very popular in physics undergrad courses to give a kind of Jamesian view of these probabilities. So say they represent our ignorance. And then people worry that, well, if this probability distribution is connected to my ignorance, somehow it's not really a property of the system at hand. But we don't have to follow Janes in this way. Instead, we can think of them as much more objective. So for instance, we could follow Mervold's almost objective view of statistical mechanical probabilities, or in the quantum case, Popescu's. So why does this, so I've tried to say that really what's going on is it's just that the Gibbs entropy is a property of a probability distribution. It's not, there's some mysterious ensemble involved. But why should the ensemble nature of the Gibbs entropy worry us? So Callender emphasizes that the thermodynamic entropy is a feature of an individual system. And so in this way, the Gibbs entropy doesn't match thermodynamic entropy. Whereas in contrast, the Boltzmann entropy is a property of the individual microstate of the system. I mean, you also need the macrostate partition, but the idea is that once you know the microstate and the partition, then you also know what the Boltzmann entropy is. And so Boltzmannians claim that the Boltzmann entropy is superior since it's a function of the microstate of the system. And that, whereas in contrast, there's this mismatch between the Gibbs entropy and the thermodynamic entropy. But I think this is kind of a bad reason to be worried about the ensemble, or the fact that the Gibbs entropy is a property of a probability distribution. And this is for the following reason. So according to functionalism, provided that the Gibbs entropy plays the right role, then other differences can be tolerated, at least for the purposes of reduction. So if being a property of an individual system or being non-probabilistic is not a part of the essential role of the thermodynamic entropy, then I think the fact that that the Gibbs entropy is a property of a probability distribution is not worrying. So that was the one part which I said, there's one bit where if you don't like functionalism, you might want to get off, but it's okay because I have an alternative reason, which I think is maybe more convincing, of why you don't need to be worried about the ensemble nature. Oh, well, one reason to get around the ensemble objection to the Gibbs entropy. So in quantum stat mech, even if we think of this probability distribution as being objective, we don't need to have any of the subjectivity of James, for instance, there's still this kind of dichotomy between being a property of an individual system versus being a property of a probability distribution. And you might think that this is somehow like, we've got the actual state of the system, and then we put this probability distribution over these alternative but non-actual states that the system could be in. So it's somehow a kind of a less good description of the system. But if we start from quantum stat mech, we never get this dichotomy between being a property of a probability distribution versus an individual system in the first place. And this is because I think that as Eddie and David and also Moroni have argued that since the density matrix is a more general object than the wave function, it should be considered to be the fundamental representation of the state of the individual system. And so then if we kind of make the analogous move, so in the in the classical case, we have the actual state of the system amongst all the possible states of the system, then we put a probability distribution over this, this set of possibilities. If we do the same thing and put a probability distribution over the kind of fundamental microstates in quantum mechanics, we just get back the same thing. We just get back another density matrix. And as such, there's no difference in the mathematical object that represents the state of the individual system and a probability distribution over it. And so in quantum stat mech, the dichotomy between being a property of a probability distribution and being a property of an individual system doesn't arise. But, and there's quite a big but, which is this. So insofar as the kind of good worry was how should we understand probabilities in statistical mechanics, there's bad news. So I think the mismatches isn't a good reason to be worried, but I do think understanding probability in stat mech is a reason to be worried. There's bad news, which is this. So understanding probability in quantum statistical mechanics is going to involve tangling with the measurement problem. And so in this way, we're sort of out of the frying pan, but into the fire. Okay, so now to conclude. I've argued that the functional role of the thermodynamic entropy is that for isolated systems, it's increasing in non-quasi-static processes, but constant in quasi-static processes. I said that the traditional Holy Grail doesn't capture the right role. It's both too weak and too strong. And finally, once we appreciate the true Holy Grail, we see that the Gibbs entropy is the statistical mechanical realizer. Thank you.
Thank you so much, Katie. It was a wonderful talk. All right, so we have some time for questions. We finished 2 minutes early, so we have hopefully enough time to answer a bunch of people's questions. The first question I have is from Gerard McCall.
Oh, hello.
Hello.
Oh, hi. So first of all, let me say I enjoyed the talk. I think it kind of jives quite a lot with my own feelings as a physicist. So that's good. But one particular about this, the idea of kind of taking the Gibbs entropy rather than the Boltzmann entropy as the better identifier. One thing I would ask about though is when you're talking about the Miner's first law and saying systems approach equilibrium, what do you mean by equilibrium here? Do you literally mean that they should approach the canonical distribution?
Yes. In this case, I'm thinking, well, I guess maybe in some cases you might want to say it's the microcanonical distribution. But yes. So, I'm imagining that. Well, sorry. I misspoke. In the case of thermodynamics, all that's happening, so the Miner's first law is like a law of thermodynamics rather than a law in statistical mechanics. So in thermodynamics, it's just saying that it reaches thermodynamic equilibrium, which is just that the macro parameters are not changing in time anymore. So the pressure and volume and other such kind of macro parameters aren't changing. But when we look at the kind of the basis of the Miner's first law in statistical mechanics, I want to say that the canonical ensemble or the canonical distribution represents those thermodynamic equilibrium states.
I mean, yes, I would agree with you that the canonical distribution then kind of it's kind of the max entropy state. But then what I would ask is, how do you then deal with something like the idea that with the eigenstate thermalization hypothesis, you know, that this kind of tells you, okay, you know, you can think of a large class of systems and however you kind of start the initial state, it's going to get to this sort of canonical distribution. But we do know that there are systems that are kind of particularly non-integrable systems, which kind of show properties like many-body localization. They don't necessarily approach this canonical state as you kind of take the infinite time limit. So how would you deal with that in terms of being able to talk about, I mean, thermodynamics in general, actually, at this point? Like, does the Miner's first law hold for those systems? And if it doesn't, then it doesn't hold for all systems.
Yeah. So I think there's this, that's kind of the question about like the scope of thermodynamics. And I think that, you know, sometimes you can find these like exotic different statistical distributions, which you can call the thermal equilibrium. But I think if those types of systems don't reach anything that we would kind of recognize as being like there's some parameters that aren't changing in time, then it seems like I would want to argue that those are the kind of systems which thermodynamics doesn't really apply to. If we think that equilibrium is going to be this like super central notion in thermodynamics.
Great. We have a couple more. Oh, sorry. Yeah, Gerard, did that answer your questions?
Yeah, great. Thanks.
Great. Well, we have time for a couple more questions, but I actually have a quick question, if it's all right, for Katie. Katie, I don't know if are you familiar with a paper by James in 1965? It's called Gibbs versus Boltzmann entropies, I think. Gibbs, go on, I'm sorry.
I think I have come across it, but quite a few years ago, so I'm not sure I'm going to be able to recall the details.
Yeah, there's an argument in it that dovetails, I think, very nicely with the case that you make. James argues that because when a system is in the canonical ensemble, the Gibbs entropy agrees with the Boltzmann entropy. They're just equal to the sort of maximum entropy the system can have. Gibbs uses this to make an argument. I guess he doesn't quite put it in these words. In similar words to you, he's not concerned with, with trying to. I guess in the paper he's not specifically thinking in terms of trying to reduce thermodynamics, statistical mechanics in quite the way that you do. But he essentially makes the case that the Boltzmann entropy is the right thing to use because essentially because if you start a system that's closed from its environment in thermodynamic equilibrium in the sense of being the canonical ensemble, in that case, the Boltzmann entropy just agrees with the usual thermodynamic entropy, it agrees with the Gibbs entropy. Then if you allow the system to evolve closed off from its environment in some non-quasi-static way, then precisely because the evolution is unitary, the Gibbs entropy, which is essentially the von Neumann entropy, it's conserved under unitary evolution, it remains fixed. But it may no longer be the maximum possible entropy the system can have. The maximum possible the system can have is if the system returns to thermodynamic equilibrium, the canonical ensemble, in which case it will agree, what he calls the experimental entropy will agree with the Boltzmann entropy again. And so you get this inequality where the final Boltzmann entropy is always bounded from below by the initial Boltzmann entropy. And the physical thing that's increasing here is the Boltzmann entropy, and the Gibbs entropy is just playing sort of a mathematical role of being constant and setting an always lower bound of what the Boltzmann entropy can be. So just say it again, initially the Boltzmann and Gibbs entropy agree. The Gibbs entropy remains constant and sets a lower bound, but the Boltzmann entropy is allowed to grow. And because it has a lower bound as the Gibbs entropy, this gives a way to understand the second law that's very similar in spirit to the argument that you're making, but with the Boltzmann entropy playing the role of the thing that's playing the functional role of reducing the thermodynamic entropy, and the Gibbs entropy is just playing a mathematical role to sort of force it to grow.
So I think that so I'm totally open to the idea that in quasi-static processes, if there's a way to show that the Boltzmann entropy is going to be constant in changing the phase space in quasi-static processes, but it's going to increase, then maybe it can also play the role. But I think in the case that you're talking about, the Gibbs entropy can increase. So the Gibbs entropy is obviously going to be a functional of the probability distribution. And the question is like, which is the right probability distribution to be using? And so have the probability distribution that's going to be evolved according to your unitary dynamics, and the Gibbs entropy of that distribution is not going to change. But you can also have your coarse-grained probability distribution. And obviously whether you can, and according to the kind of coarse-grained dynamics, so according to like things like the Boltzmann equation, then the Gibbs entropy is going to be increasing. So it sort of depends which probability distribution that you're looking at. And it's going to depend upon how you can justify coarse grain, like using this coarse grain probability distribution. And I think the way that you can justify it is not just that you pick any old coarse graining and haha, look, the Gibbs entropy increases, but rather you're going to pick the coarse graining that allows you to build one of these master equations or irreversible dynamics. And as long as you've got these kind of autonomous dynamics, then according to that level of description, you've got this new variable, the coarse grained probability distribution, and the Gibbs entropy of that will be increasing. So it kind of comes down to which is the right probability distribution to be using to describe your system.
Thank you very much. All right, so the next hand we have raised is Wayne. Wayne, please go ahead. And Gerard, if you're done with your question, please lower your hand. Thanks. And mute also. Wayne, do you want to go ahead?
Okay, now I'm unmuted. You can hear me? Good. Thank you, Katie. I really enjoyed this talk. In particular, I want to commend you for distinguishing between the second law and the minus first law, because a lot of people, when they talk about the second law, they're really talking about the tendency towards equilibration. And I think if you're talking about reduction of thermodynamics, it's absolutely essential to distinguish those. In fact, if the scope, if thermodynamics is just supposed to be the zeroth first and second laws, then you've got an easier task in reducing thermodynamics than if you have to also explain equilibration. And I don't think what Brown and UFFINK calls the minus first law was called by anybody a law of thermodynamics before the 1960s, no fairly latecomer. And this is, the whole thing is I'm very sympathetic to this. This is very, very similar to the way I've been thinking about it. So you're absolutely right. We should be looking at the functional role of entropy. And I guess I want you to say more about, you picked one functional role rather than another you could have. So you focused on the behavior of entropy in isolated systems. Not exchanging, at adiabatic transitions, either quasi-static or non-quasi-static. Now look at, and then you said something about heat at the end. Right? Now, if you look at any of the formulations of the second law of thermodynamics, they all involve some talk of heat exchange, right?
Yeah. So
another, another functional role is, just take the definition of, ds is dq over t. And so if I figure out a way of construing a heat work distinction, then that'll tell me how to get, what my statistical mechanical analog of entropy is going to be. And, the usual way to do that is, similar to the way you're talking about, you got external parameters that you're varying, and energy changes due to those are due to work. And typically we also assume you've got available heat baths, and we use a canonical distribution for those. And whether or not the system you're talking about has a canonical distribution, it can have any kind of canonical distribution, as long as the heat bath it's exchanging heat with is, you end up with the Gibbs or von Neumann entropy as the analog of statistical mechanical entropy. So I guess I'm asking you to comment a bit more about starting with isolated systems and that function, the role of entropy in that, rather than starting with the notion of heat exchange.
I agree that heat exchange is really crucial to thermodynamics. I guess the reason why I thought that adiabatic rather than isothermal processes would be the way to go is that in the case of, obviously, when you have, if you don't have an adiabatic process, then the thermodynamic entropy can decrease. And so you need to find the cases where it's decreasing. And I guess thinking, in all of those cases, you can then just apply the second law to the joint system and think about whether that and that itself is going to be an adiabatic, so your heat bath and your system. So I guess it seemed, I agree that the kind of system versus environment distinction is really central to thermodynamics, and so is the heat flow. But I thought this would be a kind of, I don't want to say easier way to go. That makes it sound like I was shirking the work, but maybe that's why I chose to go that way rather than think about isothermal.
Oh, good. I think it's actually easier if you go the other way. If you start with thinking heat exchange, we can talk at some other time.
Thanks.
Thank you so much, Wayne. So we have just a moment. David, do you have a quick question? I want to make sure there's time for an adequate break.
It's pretty quick, yeah. Katie, on your explanation of how the canonical distribution was preserved under adiabatic changes, there was a step I missed. So I can see that under the assumptions you give, then the density operator after the transformation is still going to be a function of the energy of the Hamiltonian. I didn't see why it had to be specifically the e to the minus beta h form. It looked as if that would require a further assumption that the transformation of the energy under the map was affine.
I don't know if it required that, but the additional assumption that I had was that the way that you got that you're going to have to e to the minus beta h was that the earlier and later energy eigenvalues are going to be related in a particular way to each other. I can, maybe if we don't have so long, I shouldn't share my screen again, but it was just that if it was like the earlier eigenstate was going to equal like some function of time times the later energy eigenvalue. Sorry, energy eigenvalue, the relationship between the two energy eigenvalues had to be a certain way, and then you'd get the right e to the I beta h factor.
Okay, but it's stronger than pure. I missed that. So it's stronger than pure radiolyticity. There's a substantive assumption.
Yeah, there's a substantive assumption, and I think it's one of those assumptions that everybody hopes holds, and there's only a few rigorous proofs that it does. So yeah, that's a substantive second.
I need to look at that. I won't let you share the slides right now because it looks like Jacob wants to move us on, but perhaps you send them at some point. Thanks.
Great. I think, Katie, did you say that we would be able to post your slides to the website at the end?
Yeah, I'm happy for the slides to go on the website, and also there's a paper on that's this talk's based off, which is already on the website, which has these extra details in as well.
Yeah, just a reminder to everybody that all the videos will be posted to the website, and there are some additional handouts, papers, and slides there available too. All right, we'll take I guess a 2-minute break, and then Eddie will start his talk at 2 o'clock, maybe a minute or two after 2 o'clock. So take a couple of minutes. Oh, and thank you so much, Katie. That was a fantastic talk. Wonderful, wonderful talk. Great work.
Thanks for your questions.